Hello and welcome to our webinar today presented by Dlubal Software. Today we'll be taking a look at our finite element analysis and design software, Rfem. Today's title of the webinar is Special Features to be More Competitive. My name is Amy Heilig. I'm here in our Philadelphia office and I'll be today's presenter. My colleague Lucas Sunel is today's moderator, so he'll be answering your questions. He is in our headquartered office located in Tiefenbach, Germany. Just to let you guys know, the dialog box that popped up when you logged in, you can go ahead and show and hide that control panel with that orange arrow up at the top. Feel free to ask questions during the webinar. You can use the chat option in that dialog box as well. We'll try our best to get to all of them, but if for any reason we don't, I'll go ahead and send a follow-up email. So the reason I wanted to hold this webinar today is because obviously there's multiple software options out there. Today I wanted to show you quite a few features in Rfem that I think are beneficial in terms of saving you time, making you a more efficient modeler. So whether you're using Rfem now or you're simply considering it, or maybe you're just using a completely separate software altogether, hopefully from today you'll just take away some tips and tricks to help you be that more efficient modeler. In addition to Rfem, we have all of our add-on modules, which are typically used for design, but we have a couple others that are used, for instance, RF stability, which we'll take a look at today, to help you overcome an instability. Overall, basic modeling will not be covered in this webinar. We have plenty of previous webinars on our website and on our YouTube channel that goes over those simple modeling techniques from beginning to end, so I may breeze over some of those. Also, I just want to let you guys know that although today's models are fairly simple, that's for time constraints, and I think in terms of learning, it's much easier to understand a simple model as opposed to a complex model. But you can go ahead and take what you learn from today with these simple models and apply them to the more complex structures that you have for your actual design needs. So just a few topics today. We'll be going over some efficient modeling techniques, some time-saving features. We want to address singularities. Singularities can result in an over-conservative design. As engineers, of course, we're always looking to decrease materials, to save on costs. So singularities can actually result in an over-conservative design, which defeats saving materials and decreasing those costs. I don't think there's a single engineer out there who has modeled that hasn't encountered an instability of some sort. So today I just want to show you some features in Rfem that I think help you troubleshoot these instabilities and to overcome them quickly. And today's examples, it'll be these 5 examples here. You can see a couple are more focused on the finite element surface elements, and the other 3 are more focused on beam and foundation and structures of this sort. So with that, I don't want to spend too much time on the introduction. We can go ahead and get started with our modeling. So for our first example today, I just have a simple frame here. If I scroll in, you can see our W shapes for our columns, W shapes for our beams, nothing too elaborate. It's restrained in the out of plane direction. And I went ahead and applied some line loads here. Dead load, we have 3 kips per foot. Live load, 2 kips per foot. And then I went ahead and put a wind load, a lateral load of 1 kip per foot on the structure. You'll also see here I have some load combinations that were just created according to the ASCE 7 using these 3 load cases. And then I also have my result combination. Result combination is nothing more than an envelope solution to give you the max and mins for all the load combinations that I have specified from the ASCE 7. So with this result combination, I want to go ahead and run an analysis. And it tells me that the results are not found, so it's going to go ahead and run through all of those load combinations. And if I take a look now, I have a results option down here at the bottom of my Project Navigator tab. So this is where I can actually control what I see graphically from my results. You can see here that right now I have my moments in the local Y direction displayed. and we have a max and a min, and I can go ahead and scroll through all of my load combinations here, and it updates according to which load combination was shown. I can go ahead and increase my member diagrams here just so you can see them a little bit more clearly. And we can take a look at our axial forces. Maybe we want to take a look at shears. We have stresses here. And the other thing that I also utilize in this model is we have, as I mentioned, quite a few add-on modules. So we have one called RF steel members, and essentially it's just a stress analysis of our steel members. I'm using the results from our result combination to go ahead and get a stress ratio. And you can see here that if I take a look at my colored panel list, my ratio is actually 1.11 at this intersection. So for design purposes, this obviously is not okay. We can't have over 1.0, and in some cases, maybe it's 0.8, it's 0.9. You can see the rest of the beam is relatively okay, even at these other column locations at 0.75. If I go ahead and decrease my member diagram, we can really see clearly where the problem area is. It's right at this intersection. So we have a couple options here. We can certainly increase the size of our members, but again, this can result in an over-conservative design because the only problem area is really this intersection here. So what I'm going to propose is that we maybe take a more detailed look at our intersection here with a finite element analysis. So if I go ahead and go into our wireframe view and I turn off my results, we can see here that our members are just simply 1D elements. When you're drawing a member in the program, it will only be this line, which is the centroid of the section, as a 1D element. I want to go ahead and divide this member here. So all I need to do is to right-click on the member, and I go to Divide Member, and I have a few options here, but I want to divide by the distance. So you'll take a look, you'll notice this arrow here is going from left to right, so we know where the start and the end of our beam is. So I want to go ahead and divide the member 2 feet from the end, and I hit OK. So now you can see that I have 2 separate members. And you might be thinking, okay, well, what about the loads? What happens with the loads when you divide a member like this? But you can see that the loads were also divided, but the program's smart enough to know to keep that value on the divided member as well. So we want to go ahead and do the same thing with this one. So I will divide the member by end distance. And this time, because my arrow is going the other way, or the same way from start to end, I want to go ahead and divide it from the member start by 2 feet. And if I select this column and simply hit the Enter key, the last dialog box will come up. So that's just a quick tip rather than right-clicking on the member to pull up the dialog box again. And we want to go ahead. And now we have these 3 separate members right here. So I'm going to go ahead and render it again. And I'm going to select these. And the selection is just similar to AutoCAD. If I drag from left to right, it will only grab what's in that box. If I go from right to left, it will grab everything that that box touches. So for this case, I'm just going to select here. And I'm going to choose a visibility by selected objects. So now I can no longer select anything other than these 3 elements that I specified before. So this is a pretty powerful feature that RFEM has that I haven't seen too often. If I select my 1D members and I right-click and I go to my member, I can generate surfaces from members. And now you can see, let me go ahead and put it in the wireframe view, that these 1D elements are now surfaces. So they're 2D elements now. And if I go ahead and click on the web, for this surface, you'll notice the thickness is 0.38, steel A992. All of this is taken directly from the section that you specified, the W shape. If I go ahead and select a flange down here, the thickness is 0.63 inches. So again, everything was taken from that W shape. So you might notice here that we have some geometry issues. Obviously, this is not valid. So we want to move the flanges of the column to the bottom flange of the beam. So I'm just going to hold down my Control button and select all of these nodes at once. And I'm going to use our Move Copy tool. And I don't want any copies here. I'm just going to be moving. And typically I would need to know what this distance is to move these flanges down to the bottom flange of the beam. You know, maybe after a little while I could decide, okay, half the depth, take into account the thickness of the flange. But instead, RFEM has this tool where we can select 2 points to actually get a displacement vector. So if I select from the top of the flange down to the bottom of this flange, you can see I now have a displacement vector in dx and dz. We will not be moving it in the dx direction, but only in the dz. So I hit OK, and you'll notice that everything lines up quite nice. Now, the other thing to consider is that we have this single point here where this 1D element is framing into the surface. This can actually cause a singularity. All of these forces are being transferred to this one particular point right here rather than being distributed over this entire surface. So actually what I want to do here is to create a rigid plate at the end. For our surfaces, if you go up to this button up here, you'll notice that we have quite a few shapes that you can choose from. So we have donuts, we have semicircles, triangles, anything really that you'd like to do, polygons, and the program will create this surface element and automatically mesh everything. So there's no need to individually mesh the elements. Some other programs are required to tie nodes together, to tie elements together, but the program will do this all automatically. So for this case, we're going to go ahead and choose polygon. And for my stiffness, I'm going to choose rigid. Everything's grayed out because our stiffness is super high. So here we will just go ahead and draw our plate. And once we close the loop, we can see that we have a new element here. We will do the same for this side. And lastly, we want to do the same on the bottom of the column. And I right mouse click to get out of that dialog box. And you can see now that if I go ahead and render my views and turn off my visibility node, that everything lines up quite nicely. Surfaces are only modeled at the center line of the thickness. So we do have the option in our display menu. And this display menu is essentially everything that you'll need to adjust your graphical view. If I scroll all the way down to the bottom, I have the choice for rendering here, the model, the solid model, surfaces, and I can actually fill including the thickness. And then if I zoom in, you can see that everything lines up with the 1D element to the surfaces. I will go ahead and turn that off. And now the other thing I want to show you is the Efi Mesh. You can notice that the program has automatically inserted these refinements. For the sake of this purpose, I'm going to go back to our data and go ahead and delete these. Now, if I go to calculate Efi Mesh settings, and I think most people are familiar with this with an Efi analysis, that you have to specify your length of your finite elements. Default is typically 1 foot. If I go ahead and generate that 1 foot, we can see that this is clearly too large for this situation. I mean, we only have one Fe element for the entire width of this surface here. So if we go to calculate Efi Mesh settings and change this to 0.1, regenerate the model, we can see that this is much better. And again, the program is tying all nodes together, all lines, so you don't need to worry about any of that. Okay, so one last thing to consider is our loads. For our dead load, as I mentioned before, we kept these 2 member loads, but in this case, we actually don't have a member here anymore. We have a surface. So we need to go ahead and delete these, and I just click on the load and delete them. And I'll apply a line load instead. So line load is very similar to a member load, except for it can be applied to surfaces, for instance. So for here, we want to go ahead and apply -3 kips per foot. I just simply zoom in and click on my lines, and now you can see that the 3 kips per foot has been added. I want to go ahead and adjust my live load. If I hold down the delete key and click on each load, that will also delete those loads. Again, I want to draw a line element, and because I'm in live load up here, that is where the load case that this load will be generated into. So for this one, I want to go ahead and specify it as -2 kips per foot. Again, I just scroll in here, and we have our loads. Okay, so I believe that we are ready to run our analysis. I want to go to my result combination again, and I'm going to go ahead, and it's asking if the results are not found. And up pops our dialog box. This will take slightly longer than, of course, our 1D elements because we now have the 2D surface elements. And you'll notice here that it's just simply going through each iteration as the load increment increases as well. So instead of the members, which you'll notice that the member diagram stops short of those surface elements, which is fine. I'm going to go ahead and turn that off, and I want to actually take a look at our surfaces. If I scroll in here, now I can view all of the different internal forces for the member, shears, moments, everything of the sort. What I'm really interested in is the stresses. So I go ahead and view the von Mises stresses. Everything looks okay until I zoom into these points. We can still see that it's extremely overstressed. So we have an option here where maybe we want to add a plate to this bottom flange, maybe an inch plate. So if I go ahead and I turn off my results and I hold down again, select this surface and hold down the control key, then I can just go ahead and select all of these bottom flanges. Now I can right click. Oh, sorry, I lost it. Let me go ahead and do that again. Okay, now I can right click, edit surface, and let me increase my thickness now to 1 inch. And in the rendered view, we won't see that unless we go ahead and change it to the thickness under our display options. And you'll see that it's slightly thicker than our 1D element, which is exactly what we want. And I'm going to go ahead and change it back to here. Now, the other option now is to actually do a plastic analysis. With our add-on module, MatNL, which takes into account nonlinear materials, we can go ahead and select all of these, right-click, edit our surface, and we want to go ahead and create a new material. So I go in here to my materials dialog box, and you can see that the library is full of quite a few materials. Of course, we can go ahead and filter them according to metal, steel, ASTM, but more importantly, we have this option on here, our favorites group. So with the favorites group, you can just simply save the ones that you use the most often. And for me, I just created one USA, and I'll use steel A992. Now, the material model, the default is isotropic linear elastic, but for this case, I actually want to use isotropic plastic 2D, 3D. Up pops this other dialog box. You can see our stress strain diagram, and we have our yield stress here, 50 KSI, which is automatically filled out, and our strain hardening modulus. So here I can go ahead and click OK. Everything looks fine with that. I hit OK, and I hit OK once more. And I zoom out, and we're, if you're not quite sure if the material is different than the rest of them, you'll notice here that I'm actually in my table down here, and I have this steel A992, which is isotropic linear elastic, and as I highlight the field in the table, the members themselves will actually highlight as well. This blue one just means that it's not being used currently. And then the steel A992, plastic 2D, 3D, you can see that those were actually applied to here. Okay, so I want to go ahead and run my result combination again. And again, this will take slightly longer than the last one because now it's a nonlinear material. And keep into account the size of your mesh also matters for your finite element. at some point, the smaller mesh you go is not going to change your results. So what I would suggest is to keep a mesh that doesn't create a super long solve time, but will obviously give you the accurate results. You'll notice that if you decrease the mesh size and solve again, your results won't change by much. We also have this graph here that shows the maximum displacement as the program is cycling through each iteration. So as soon as this is done solving here, which will be just a second longer, and again, it's just because we do have a nonlinear material. Now I want to take a look at these contours. Each FE element actually has a value at each corner. And what the program is doing is using a smoothing algorithm to tie all of those values together and to create a nice smooth diagram. Under my display tool, and I scroll up here to my results, I actually want to choose constant on elements. Now what this is going to do is this is going to actually average out the 4 values for each FE element. Then you can take a look individually for each FE element. And you'll notice that nothing exceeds 50 KSI, which is our yield stress, which is exactly what we'd expect. I think an important thing to show you here is that we have an option under results called criteria. And this criteria will actually show us our FE elements that are in their full plastic state at 1.0. These other 2 green ones are obviously somewhere in between 0 and 1 as the ratio, and then the other elements have not reached that state yet. So that simply concludes our first example. I want to go ahead and move on to our next one, which again is very simple. It's just a continuous timber beam, 3 spans, nothing too special about it. But actually what's going on behind the scenes is quite powerful. And the purpose of this example is to actually show you the use of parameters or parametric modeling. So if I go ahead and go to edit parameters, and I move this dialog box down, with parameters, you can actually define a variable in the program and then use these variables in an equation to change the span lengths, to change loads, to change angles. There's quite a few options, which if I show you here, we can change areas, angles, surface thicknesses. So I'll get into that in just a minute. But if I go ahead and type in 2 meters here, and then for my B length, which would be my second span here, I'm going to go ahead and type in 5. And maybe for my C length, I'll go ahead and type in 3. I hit apply, and you'll notice that everything is updated. Support's removed, and I also want to show you that if I go ahead and look at my dead load, everything was adjusted with the loads as well. We have separate live loads on each of these spans, and those were all updated as well. Now let's say I want to edit my live load to, let's say, -2 kilonewtons per meter. And I go ahead and hit apply. You'll notice that now the live load was updated. So you can understand the benefit of using parametric modeling for a company that maybe creates a lot of the same structures, but of course geometry is changing slightly, maybe some loads are changing slightly, but overall you can use the parametric modeling to deal with structures that are very similar to just improve your efficiency. Now, the other thing I wanted to show you is if I go ahead and, again, I created quite a few load combinations from the ASCE7. If I take a look at my result combination, and it's asking me, do I want to go ahead and run the calculation? Yes. So this is just finding the max and mins of all those load combinations. And now I want to take a look at my support reactions. You'll notice here that as I scroll through them, of course, my support reactions are changing according to the different loads that I have. Now, I want to show you guys our print report option and including these parameters. I think that RFEM has quite the powerful print report options in comparison to a lot of other software that I've even used in my design career. If I go ahead and open up a printout report, and I created one previously shown here, a separate dialog box will actually open. You'll notice here on the left are our table of contents or report navigator. I can click on these and our report will actually update according to where I am over here. Now the same goes for here. I can keep scrolling down and the table of contents will also update over here. And I went ahead and put in some pictures here of our support reactions. And you can see this is reflecting our spans that we currently have, which is 2, 5, and 4, I believe. And they're for each load combination. If I go ahead and zoom in here, I can see load combination 3, my support reactions, my max, my min. Everything has nice headings. It's very clear. But let's say, oh, okay, well, my beam just changed all of a sudden. So I'm going to exit out of this print report. No, I don't want to save it. I'm going to open up my parameters, which down here in my table under my first model data tab is a quick link to my parameters. And let's say I want to do 5 meters, 2 meters, and 3 meters. I hit OK, and then you can see that everything was updated. Now, I want to go ahead and run the results again. And I go back to my print report. And now I want to go ahead and jump down to these pictures, and you can see, well, it looks like we are missing our support reactions. Well, regardless, I think that we can see that from our results here, we have the support reactions shown, and it looks like they're shown here. And it should go ahead and update in our printout report. I'm not quite sure why, but regardless, the geometry is taken into account. And everything in the print report will be adjusted according to your changes that you just made here. I can go ahead and showcase this a little bit further with the printout report by taking a look at our members. I'm going to turn off my support reactions, and I just want to go ahead and view my moment about the y-axis. Of course, as I scroll through, oh, that was probably the issue. I didn't run a result combination. So again, this is just an envelope solution of all the load combinations, and I think that's why the print report didn't show up, because I didn't run all of them. I can go ahead and scroll through each load combination for the moment about the local y-axis. I go ahead and increase these. And let's say I wanted to print off this moment for each load combination. Typically, you would have to take a picture or a graphic, insert it into your PDF print report, go back, change the load combination, do the same thing. But we have an option in here called mass print. If I go ahead and go to my print option, graphic printout, I see the mass print here. Now I can go ahead and hit these settings right here, and I have 3 tabs that pop up: model, loads, and results. I'm currently in results, and the program knows that I'm looking at the moment about the y-axis. But for my load cases and combinations, instead of the current one that I'm in right now, I'm going to go ahead and select all. I hit OK, and now the program's cycling through each load combination for my moment about the y-axis, and it's going to go ahead and insert those into this print report automatically. So you can see now that my support reactions were updated. I just needed to run my result combination. But if I go ahead and scroll in here, I can see that now I have my load combination 1 with my moments, and it shows my max and my mins. Scroll down, load combination 2, load combination 3. Everything is done automatically. So I think you can imagine how much of a time saving that is when you can use this mass print option. Okay, so the question is, with parametric modeling, how do we actually incorporate these parameters into a model? So for the sake of time, I have already created this simple beam, and I've applied some loads on it just according to dead load and live load. And I want to go ahead and edit my parameters. Now if I type in A for my first span length, the length automatically pops up and we'll just do 3 meters. B for my second span length, we'll do 5 meters, and C for my third. Now you notice nothing in the model is changing right now. I'm just simply defining what parameters I want to have in the model. And we'll go ahead and make this one 4. Now let's say we also want to consider dead load. Now instead of length here, I actually want to go down, and this is where I told you before there's quite a list to choose from for the amount of parameters you can actually define. Precambers, moments, stresses, time, mass, percent. So we have quite a powerful option here when it comes to parameters. For this case, I'm just going to go for a line force, and I will go ahead and do -4 kilonewtons per meter, and maybe my live load, again a line force, and I want to do -2. Okay, so now that we have our parameters defined, we need to actually apply them to this model. So for node 1 here, actually it's node 2, we want to go ahead and edit it. So to edit it, all I need to do is just double click on it, and the dialog box pops up. My coordinate X here is just a static 4 meters. So I want to incorporate that parameter in there. So I can actually click on this little box here. I have the option for a calculator to measure. Full precision is just increasing the decimal places. But instead I want to choose edit formula. Then we have all of our parameters available here. If I double click on A, I check it. Now you can see this little yellow highlight. It's telling me that it's using a parameter to define my X coordinate. I hit OK, and now that should be dependent on my parameter. Before I do the other ones, I want to go ahead and just quickly add some dimensions to this. And just like AutoCAD, you can just click on each node and bring down the dimensions. Let's say I want to add my unit. And now I can see visually the span length between these different spans. I go ahead and do the same thing to this node. It's set at a static 9. I want to edit my formula, and I'll do A plus B. And now, again, it's dependent on those parameters. And lastly, I want to do this one, and I will go ahead and edit my formula, A plus B plus C. Okay, so everything is now dependent on my A plus B plus C. Now we also need to do the same thing for our loads, and we can go ahead and highlight all of these. We right click, edit member load, and we can go ahead again the same way that we define those node coordinates. Instead, here for the load parameters, for the actual value, I can use this arrow, edit formulas, and choose my dead load. I hit OK, and now that dead load is dependent on that parameter. Now we just need to go ahead and do the same for each live load. And so instead of dead load, I'll go ahead and choose live load here, hit OK, and I do the same for each span. Edit my formula, add my live load, hit OK, and lastly I have this one. Okay, so now if I go ahead and move this up and I open up my parameters, I change this to 2 meters, 3 meters, 6 meters. We should see that everything is updated just fine. For our live load, we'll go ahead and choose -6 and apply that, and everything is updated. So you can see that this is obviously quite valuable, again, for a lot of the similar structures that you're working on, or maybe it's the same structure and there's a lot of changes going on within the design process. So that sums up that simple model. So we'll go ahead and move on to the third one. This one is a little bit more complicated Efi analysis with our surface elements. And I also created this model to have parameters in it as well. So you can see here I've defined my parameters, my angles, my loads within my pipes, which you can go ahead and define a pressure load within this pipe and maybe the spacing between. If I go ahead and change this to 30 degrees and I hit apply, you'll notice that this pipe automatically changed to 30 degrees here. One thing to take note is that this is an intersection of surfaces. And you'll notice that when I changed this to 30 degrees, everything was updated. There's no need for me to change my FE elements. I don't need to go back and change the geometry. The program's smart enough to make all of those changes as I go ahead and adjust the model. I can show you guys again, if you take note at this 50, I can go ahead and change my angle right to, let's say, 70 degrees. And I'll go ahead and hit apply. Again, everything is updated automatically. I even have the ability to click here and right click to edit the component's parent surface. And we have a pipe option here. And I can change my radius to 2 feet. Again, everything is automatically updated. Those surface intersections are moved up and everything looks quite nice. We can do the same here. Maybe make this radius a foot, hit OK, and again, everything looks okay. So I want to show you guys how to go ahead and create this model and create an intersection of surfaces. So I'm going to go ahead and open up this beginning model, and all of these are just line elements. They're not members, they're just simply lines in the program. I can define maybe members out of them if I wanted to, but in our case, I'm going to go ahead and apply a pipe surface. So I'm using these quick tools up here, and you'll see there's an option for pipe. Maybe my material when I first open it up is something like concrete, or maybe it's even timber, just something not applicable. So I can go in here to import a new material from my library. And again, for even metal, steel, ASTM, we have tons and tons of materials. I want to utilize my favorites group again, and I'll just go ahead and choose my steel A53 grade B. My thickness for my pipe, we'll just go ahead and set that to 0.6 inches. And now we need to go ahead and click on the pipe tab up here and choose our radius, which we'll just do 1 foot. Now you'll see that the program automatically applied it to this line because I had it selected when I went into that dialog box. I want to go ahead and do the same for these two elements. So I can go in here to my pipe surfaces again. And again, you can hit the enter key and it will bring up that same dialog box, which is a little bit time saving. For my thickness here, I just want 0.2 inches, and my radius, I'll go ahead and set it at 0.5 feet or 6 inches for these smaller strut pipes. Then all I need to do is just click on those lines and everything's created. Now, you'll probably see that we have some issues with our geometry. Same thing as the first one, we have some intersections here that we need to take care of. So what I actually want to do is to select everything, and I'll right click, and for my surface, I want to go ahead and create an intersection. And the program will automatically intersect all of these surfaces that I have selected. Now they're all just surface elements, but again, we need to take care of this geometry. So I'm back in my data navigator for this model, and I can actually go to my surfaces here. And if I expand my surfaces and I click on them, you can see as I scroll down the list that it's actually highlighting each element that I'm clicking on in the graphic view. So we get to this component right here, and we do not want to consider this in our analysis. Typically, this would not be a realistic situation. So we can right click here, and we can actually deactivate the component. So you'll notice here that it says inactive, and it's gone from our solution. I can go ahead and do the same thing for this one, deactivate, and I also have the ability, of course, to activate it again. But for right now, this is exactly what we want. Now, just like the first model, we need to go ahead and create some rigid end plates here. And instead of the polylines, I'm going to go ahead and select a boundary line. I want to go ahead and select rigid here. And all I need to do now is just simply select these circles. So you can see how easy it is to apply surfaces in Rfem. It's just simply the click of a button. I can right click to exit out of that. Now the next thing that I need to do is to go ahead and apply some support. So I'm just going to click on New Nodal Support. And maybe I don't know what this is, so I want to go ahead and create a new one. And you'll notice here that we have a lot of nonlinearities available. Maybe you have sliding, maybe you have friction, you can define your own diagram. So quite a few options here, or we just have the typical linear nodal supports. And for my case, I'm just going to go ahead and restrain it in the X direction and in the rotation about the X, and then in the X, Y, and Z direction. I can go ahead, hit OK, OK, and all I need to do is just click on these nodes. So lastly, I want to just create a simple load case. Let's just do self-weight. So I'll call this load case description dead load, and I just want to activate self-weight. And now we just have this single load case, and we can actually go ahead and view our results by running the combination. Actually, I forgot one thing I wanted to mention. Let me clear these results. I mean, you can see it right here. You can see our Efi Mesh is not ideal. It's too big, and you'll probably find as you decrease this that your results are going to change. So again, when I go to calculate Efi Mesh settings, the default is 1.0. So for larger structures, this may be completely adequate. But for a smaller model like this, let's go ahead and change this to 0.25, and we'll regenerate our model. And that looks quite a bit better. You also have the ability to go ahead and add an Efi Mesh Refinement, let's say around this area, around a line. And what that will do will to actually decrease your mesh size only around this area without decreasing the entire model, which can significantly save on solve times. So let me go ahead and run that analysis again now that we have a better mesh. And we're only running dead load, so it should just take a second. And now we can see that we are viewing our von Mises stresses for the pipe. Again, similar to the first example, maybe we have some higher stresses here that we want to address. We can certainly view our deflections, which is actually only 0.001 because it's only self-weight. So I'm not going to do the parametric modeling because we went over that in the last example, but you can see how powerful surface elements are in RFEM and how easy it is to apply them. Okay, so moving on to our next example is just a typical foundation. It's a concrete foundation. If I go ahead and double click on it, I just have defined it as 4,000 PSI concrete. It's 12 inches thick, you know, maybe a foundation or an elevated slab, something of the sort. I also have applied a few loads here. Just your typical dead load in KSF 1.5, maybe a live load of 0.75. And then I also have a couple load combinations here according to ASCE 7. Then I also have the result combination for the envelope solution. Now I've also utilized our add-on module RF concrete surfaces. What this will do will to actually tell you your reinforcement that's required according to whichever load combinations you choose. I went ahead and ran RF concrete surfaces according to my result combination because I want the max internal forces to be used for the design of my reinforcement. So I can go ahead and solve here, and I already had them saved. If I go ahead and look at my ISO bands, I can see here from my RF concrete surfaces, and I'm looking at my required reinforcement. I can zoom in. Everything looks okay except for these nodal supports. They look a bit high. The same, I can go ahead, go back to my result combination. I'm looking at my surfaces, and let's say we want to look at our MX. Again, you can see there's much higher moments at these locations of nodal supports. MY, the same thing. We can take a look at our stresses, very high stress concentrations at these locations. And this was a situation of a singularity, essentially, that we want to address. If we don't address this, then we will have a much too conservative design for our reinforcement. So if I go ahead and turn on my grid, and my grid settings are down here. I can just snap that on. I can right click and hit edit, and I actually have my grid set up right now to dynamically according to the size of the model. So it'll just move with me as I am doing my modeling. We have a feature up here called define a section or results diagram. So what this does, if I go ahead and click on it, and I want to define a section right down the center of this where those nodal supports are, and up pops this results diagram. So essentially, this is going to be just a section cut right through where I defined it, and you can see that my values are changing as I'm scrolling over the length. Right now we have deflection shown in inches. Down here are my stresses. Maybe I want to view the MY. You can see that everything is significantly high right here at this nodal support. So this is the singularity option that we want to address. Up here, I can scroll through my load combinations, and I want to take a look at maybe my required reinforcement. I mean, we're up near 5.93 inches squared per foot at these locations. Everything else is relatively low. So we do need to address the singularity. I'm going to go ahead and save this section as midsection so that once I exit out of here, and I'll go ahead and turn off these contours, now I can view my results as this save section. I can go ahead and scroll through load combinations to take a look at anything that I want to view here. And let's see. So how do we deal with these singularities? We have a couple options in the program. The first is we can actually consider a column support here with the correct spring stiffness to distribute the load to all the surrounding Efi elements here. So rather than just all of the load being placed on these single elements or these single node points, we can actually distribute the load. And I think this is a pretty cool feature of Rfem, again, that I haven't seen too often, but we can actually go here to a new nodal support. I'm going to go ahead and create a new one. And instead of using these definitions down here, I can create elastic support via column in the Z direction. And up pops this edit column. I have three options here. I have an elastic surface foundation, which you can see our springs here are being tied to the Efi elements, an elastic node support so that it's being tied to a single node, or a node support where it actually adjusts the stiffness of the Efi elements as well. For our case, we're going to use an elastic surface foundation. Let's say our column or our pier framing into it is circular with a diameter of 24 inches. And let's say that I want to go ahead and define this column height as 7 feet, and maybe support conditions at the column base is rigid. Now you'll notice here that everything has updated according to the stiffness, the spring stiffness, and these parameters that I've entered in. It's based off 4,000 PSI. So as you change this, you'll notice that the springs are actually changing as well. So if I go ahead and hit OK, it's asking me my Efi Mesh will be clear. Do I want to continue? Hit OK once again. Now I can apply this to here. And you'll notice it looks slightly different. It has a radius here so that we're actually applying those spring stiffnesses to that support. Now, if I go ahead and run my load combinations again, and this will actually be running the concrete add-on module to take a look at my required reinforcement. So if I mean, we can see it visually here. Let me go ahead and turn off my grid. If I go ahead and select midsection here, I right-click, go into my results diagram. Now we can see that it is now undefined. We're only defining our reinforcement up to the surface of that column, up to the face of that column, which makes sense. This is typically what you would do. Now we can see that the surrounding reinforcement required is much, much lower, but we're still looking at this singularity on the other node, which is exactly what I wanted to show you guys, that how much our required reinforcement has decreased. So I want to go ahead and scroll back to our results combination. Again, I wanted to show you guys deformations don't really matter, but our stresses, again, are significantly lower at the face of the column as compared to the single support over here. If we want to take a look at MY, we can scroll down here. undefined right here, still significantly high. So that is one way to deal with that singularity. Now we have one other option. If I go to my data and I expand on the model I am in, and I can go ahead and look at my average regions here. If I right click and do a new average region, then this will actually, I can define my, first of all, I want to define my surface. Then I want to define, okay, where do I want to average out these regions? I want to do this point support here. Maybe I want it to be circular, and I want the dimensions to be, I don't know, let's say 3 feet in this case. Now, what it's doing is it's going to average out in both the U and the V directions, which we have a nice picture here to show us exactly what all of these mean. And all of our internal forces will be averaged out within this 3-foot radius. I go ahead and hit OK, and I want to solve once more. And you can visually see here that our average region is shown. So now we can see that our reinforcement is down to 3.64 inches. And again, we can go to our result diagram and see that that has been reduced. It's still higher than this other one because we aren't defining anything at the face of this column, but it is significantly lower in comparison to where we were. We can go into here, into our RC1, and we can take a look at, again, our von Mises stresses. Sorry, I have this other one shown here, but you can disregard that. Much lower than what we were looking at before. And we can also see, let me go back to here. We can also go ahead and add in our MX, much lower than what it was before. The other quick thing I wanted to show you, if I turn back on my grid here, we have a powerful feature in Rfem which is called drag and drop. Let's say I wanted to copy this section over to here. All I need to do is to highlight it. I push down my control button. Now I just drag it and drop it. And now I have another section here. Let's say I want to go ahead and do the same over here. And now I have 3 sections. You can go ahead and we can run one of these load combinations. And now you can see that I have these sections at all of these locations. And what I wanted to show you was that essentially drag and drop can be used for anything. Let's say I wanted to move this support here, or maybe the edge of this surface. I can simply just, it's asking me if I want to clear my Efi Mesh. All I need to do is just to drag out the corner of that surface element. So you can understand that that's a pretty powerful feature instead of using the move option. You can also click on something, hold down the control key, drag and drop it, and it's just a copy. And you'll notice that my grid went ahead and expanded with it. I mean, I can do multiple elements. I hold down my control key, and I can move everything over to here. So all the dimensions and everything we're moving as well, but you can understand how much of a time saver that can be rather than using the copy move tool every time. So lastly, I want to move on to our last example, and we will go ahead and open up this Parametric Hall. It's a simple Hall, and to let you guys know, of course, we have this under Tools to generate model members. You can create quite a few different structures here. The continuous beam I used for one of our examples earlier. I didn't showcase it, but it's possible to do continuous beams, but more complex 3D frames, 3D halls can be created. If I go ahead and click in here to create a 3D hall, you'll notice that I can define all my geometries. It's laid out very clear here in the picture. Any bracing that I may have, I can define my cross sections, and I would hit OK, and my 3D hall would be created. This one is also based on parameters. Let's say I wanted this to be 15 and maybe another 15. Oops. And I go ahead and hit apply. Efi Mesh will be cleared. Everything adjusts quite nicely. Let's say I want the angle of my roof to be a little bit higher. Let's say 25 degrees. And I go ahead and hit apply. Now the roof angle is changed. So again, just another use of those parameters. I'm going to go ahead and undo this. Okay. So with this Parametric Hall, I went ahead and added in some simple loads. Again, we have our dead load. Now we have some snow loads on here, and I used our snow load generator. If you go to Tools again, Generate Loads from Snow Loads, Dual Pitch Roof, ASCE 7. Now you can see all I need to do is just define the roof geometry and then the factors from the ASCE 7. And the program will go ahead and create 3 load cases, balanced, unbalanced, and unbalanced. And it will automatically put them in as load cases into the program, which is what I did here. I have LC2 snow load 1, here's snow load 2, here's snow load 3. And then I actually put in some imperfections here. Imperfections can be used for out of plumbness. Maybe we have a pre-camber, and I just wanted to showcase this to you guys to let you know that it is possible to take all of these into account. They are dependent maybe on the normal forces in the program, and everything is done automatically. You just need to define your inclination and your pre-camber. I have my load combinations here according to ASCE 7, and it includes all of these imperfections as well. So let's take a look at this first load combination, and it's just 1.4 dead plus my imperfection. I go ahead and run it, and it begins to run, then all of a sudden I get this instability. You know, it's an error message. As I mentioned, we all have seen these. However, down here in this explanation, it tells me the specified load is greater than the critical load. And what's really unique about RFEM is that there's actually a big red arrow telling you where this instability is taking place. That can be extremely helpful for large models. So it's telling me that my specified load is greater than the critical load. I say, okay, now I need to go ahead and address this. So with load combinations, everything is run according to a nonlinear analysis and taking into account p-delta effects. But for load cases, they are run as a linear analysis. Only load combinations will go ahead and apply those p-delta as a nonlinear and adjust that stiffness matrix. So for load case 1 dead load, I want to go ahead and run it just to make sure that maybe my geometry is okay, I don't have any nodes not connected. And I go ahead and run it, and everything runs fine. You can see here that I have my results diagrams pop up for my moments about the local y-axis. So, okay, it has something to do with those secondary effects. So what I want to utilize here, which I mentioned to you guys before, is we have all of our add-on modules down here under our data page. Quite a few options to choose from. I added a few here to my favorites list, and what I want to utilize today is RF stability. So if I go ahead and open up RF stability, this will actually show you the eigenvalues graphically of the behavior of your structure. Even if you can't solve it like I just showed you with that instability, we can go ahead and show the behavior of the structure and also the critical load factors that will, you can multiply your load, your applied load by before you will see that buckling behavior. For this case, I want to go ahead and set my eigenvalues to 4. And the load case that I chose is just my dead load. There's quite a few other options in here. I don't really want to get into it today. It's a little bit more complicated. So we'll just go ahead and calculate. Now the program is still in this add-on module, and now we can see that we have our critical load factors for the 4 eigenvalues. This is purely interpolation, that the applied dead load I can multiply by 1.17 for this eigenvalue before it reaches its buckling behavior. If I go ahead and go to my graphics view, and I want to take a look at my first eigenvalue, and I go ahead and play this animation, well, we can see that this column here is buckling out of plane. Let's take a look at the second one, and the whole structure is racking. If we take a look at our third one, it looks to be that column again, buckling in the other direction. And lastly, for our fourth eigenvector, still the problem column. So what we want to do is to go ahead and address these columns in here. So if I go ahead and select, let me go ahead and turn off this movie, and I go ahead and select all of my columns in here. I hold down my shift key to make sure I've selected all of them down here, and I right click and I go to edit my member. Essentially most things that you need, if you right click, have something selected and right click, there will be most of your options. So for this one, I want to go ahead and edit my member. I see that these columns are a W8 by 58, which is extremely small. So maybe we want to consider increasing the section size. So I can just go ahead and modify here. And I'll again modify my shape here. And it brings up all of our cross sections. I have my favorites group activated. So I'm just only looking at the AISC shapes. And let's say we want to maybe go ahead and select a 10 by 68. Still A992 is fine. We can always modify that here as well. I hit OK. OK. Do I want to clear my results? Yes, I do. And I hit OK once again. So now I'm going to go ahead and run load combination 1. And with this new section size. And you can see now that we are getting results. So again, RFEM can be really useful in pointing out where exactly that instability is occurring. Not only that, it can be used for a stability analysis with RF stability to show you your eigenvalues and your critical load factors to go ahead and address the buckling behavior of any members that you may have in your model. Okay, so that is the end of our presentation today, and we went through these 5 models. And I want to encourage everybody, of course, to visit our website. We actually have redone the entire website as of the beginning of the year. So I think you'll find it a little bit more modern and easy to move around in it than our older website. You can find plenty of videos on there, links to our YouTube page. The Dlubal blog is just frequently asked questions. If you guys want to go ahead and email us, it's just info-us@dlubal.com, and our phone number here in the Philadelphia office, we're available, of course, Monday through Friday, is 267-702-2815. We'll have plenty more webinars coming up this year in 2016. We try and do one about every month. You can go ahead and register on our website. Or I've been sending out email notifications, so certainly continue to check those. If you guys are interested in PDH, go ahead and email me which state you're looking for, since different states have different requirements for the certificate, at this email here, info-us@dlubal.com. And I'll be happy to issue certificates to everyone in attendance today. And with that, I just want to thank everybody, and I hope you enjoyed the webinar today. Certainly let us know if you have any questions, and I look forward to seeing you at the next one.